Alright, so in this video we're going to look at our final quantity in the rotation unit, and that is angular momentum. So we are going to party Michael Jackson style because this is the last bit of the rotation unit. Woohoo! Alright, so angular momentum. So if you think about some of the things we've studied in rotation so far, they've all been congruent to linear quantities. So earlier this year we studied linear momentum, and that is the quantity of the mass times velocity of the center of mass of a rigid body moving through space. Now, when we have an object that's rotating about some axis, those particles are also experiencing rotational movement and therefore what we call angular momentum. So the quantity angular momentum of an object rotating is similar to linear momentum in that linear momentum is the mass of the object times its linear velocity at any given moment. And these are also vector quantities where mass is a scalar and momentum and velocity are vectors. Therefore, they are aligned in the same direction. The angular momentum, capital L, of an object rotating at an angular velocity, omega, is going to be proportional to the moment of inertia I, just like mass is proportional to the linear momentum P. So L equals I omega, where L and omega are also aligned in the same direction. Now the units for angular momentum, units for I are some of the mr squareds, which is kilogram meter squareds, times omega, which is standard units of radians per second, but radians is just a ratio of mass to mass, so this becomes kilogram meter squared per second. Those are your standard units for angular momentum. Now, if I want to change the angular momentum of a system, I'm going to look at it just like we did with linear momentum. And what we saw was the impulse on an object was when a force acted over a certain period of time, and that changed the linear momentum P of that object or that system. Now, the same thing will be true with angular momentum, but this time it's an external torque, tau, or the net external torque, sigma tau, times the time period will equal the change of the angular momentum of that object or system. So external forces cause changes in linear momentum. External torques cause changes in angular momentum of an object or system. Now, what if the net external torque on a system is zero? This is would be what we would consider a closed system. All torques are internal. So when we have a closed system, just like we did in linear momentum, a closed system, the internal forces did not cause a change to the momentum of the system, since the sum of the external torque forces in that case would be zero. Same thing when the sum of the external torques is zero. In this case, angular momentum is what we say a conserved quantity, or the conservation of angular momentum. So meaning, no external torques, the angular momentum of the system stays the same, therefore delta L is zero, meaning L final minus L initial is zero, L final equals L initial, or I omega initial of this object or the system has to equal I omega final of the object or the system. So let's look at a couple examples where we have a system that's closed and we have a change in one property of the system and see how it affects the other. So namely, we're going to be looking at situations where either omega is changing or I is changing. And if it's a closed system, then omega or I is going to increase or decrease to compensate for that change. So in the first one, let's look at an ice skater who's spinning, and they pull their arms inward closer to their body. Well, when they pull their arms inward, they're going to have some initial omega and some initial moment of inertia. And when their arms go inward, their distribution of mass about their point of rotation, their axis of rotation, will decrease. So if I decreases, then omega has to increase in order to compensate so that angular momentum can still be conserved. So that's why when you're spinning, or when you watch the Olympics and you see the ice skaters spinning around. As they move their arms in and outward or their legs in and outward, they actually change their angular velocity because they're changing their moment of inertia about their point of rotation without an external torque. So a child now walks from the edge to the center of a merry-go-round. So if a merry-go-round's rolling around like so, and you have a child with some mass, and they're part of this system. So the system would include the child and the merry-go-round. And they walk inward. The effect that they have is that now the R goes down. Again, you're decreasing the moment of inertia of that system. Therefore, you will increase the angular velocity. What about an air mass that's on the outer rim of a hurricane, and that air mass is drawn inwards towards the low pressure eye of the storm? So in this case, we have mass drawn inward, distribution of mass decreases, moment of inertia decreases, and therefore the rate of rotation of the storm increases. So as a hurricane sucks more and more mass inward, you see an increase in the wind speeds due to this conservation of angular momentum. All right, what about a diver that's jumped off a board, they're rotating in a tuck, and then right before they enter the water, they stretch outward and elongate themselves before entry. In this case, you're going from close distribution to a longer distribution about the axis of rotation, so the moment of inertia increases. And as the moment of inertia increases, your angular velocity decreases, and they slow down in their rotation so that it's safer and they have a better chance of making a good entry into the pool. So there are some conceptual conservation of angular momentum problems. In the next couple videos, we're going to look at some examples.